So let me first rewrite these axioms, because just to have them ready, we may need them later on. So first of all, we have a subset of some Euclidean space, and then we have two groups of axioms. The group 1 should be considered as being topological. That means it could be treated separately, and this is what will happen later on. So there is a locally finite to make this clearer, a locally finite partition. And the partition is a set of subsets. So I write it tautologically of W. That is the first axiom. So we decompose into, you could at this level call them pieces, which is not unusual, into pieces. And the second axiom was the condition of the frontier. That means if you take the closure of a stratum minus x, this is well defined because everything is contained in our mu and takes the induced topology. This is a union of strata y in a certain subset. So here we can say y bar intersects and of course these cannot intersect x. They must be different from x by this condition. And then we have seen certain consequences of this. So these two together, seen abstractly, so you have a topological space with these properties, would describe a decomposable space. And we would have here, again, this order relation I described. But knowing these axioms, it's only a pre-order. It's not a partial order. Or Bourbaki calls this an order as such. But there's a different use of language. So that means x less or equal y and y less or equal x does not imply that y is equal to x on this level. But with it is really condition B which does it. So this is topological setting. And the second group of axioms could be called, it's not really analysis, it's differential, let's say geometry, even though there is no metric, but it is really geometric thought behind it. First of all, the pieces are embedded submanifolds. Here's an embedded submanifold of our mu for all x. This is relatively harmless and very common actually. And the second is the condition B. If x is less than y, and x a point of x, and then we have two sequences. So one sequence in x, which converges to this point. So it's a point in a submanifold. And the other sequence coming from the big stratum. And now we need two conditions. Let's say call this the condition A, which actually is why this nomination occurred. The tangent spaces at these points converge as n goes to infinity to some space tau. And since we are in Rn, this is completely unproblematic. You take the orthogonal projections on these spaces, and then you have to assume that this projection converges. Since this Grassmannian space is compact, you can always extract sequences, subsequences, such that you get convergence, but you may well have two limit points or three. This means you want convergence. This is not a serious condition. And then you introduce the connecting line or secant between xn and y, which is well defined because these two have to be different. So we could take the unit vector which converges by assumption to some vector L. Again, I mean, you always have convergent subsequences, but it's not clear that it converges. If these two conditions are satisfied, then we have L is an element of tau. Now this is the and as we did study last time a little, oh no, there it is. This is a mysterious condition because it's not satisfied for the slow spiral, but it's satisfied for all the fast spirals, and you ask yourself, what is going on here? This is such a subtle difference. The topological aspects for both are absolutely the same. So this needs more thought. I wanted to discuss the example that Marcus just mentioned, the umbrella, as the third example, the Whitney umbrella. Just to give a flavor of why you can actually verify this condition B and how. Yeah, so we have defined this space W, which is contained in R3, as the inverse image of 0 under a smooth function f of x, y, z is equal to x squared minus y squared times z. So this we know. And we also know that this is a singular space because the is equal to 2x minus 2y z and minus y squared. And if y is, so we should say this is equal to 0 if and only if x is equal to plus or minus y times the modulus of z, and z is greater or equal to 0, because if z is negative, this has no real solutions. So this is an interesting point, and then we can actually write it like this, because otherwise it's not in the 0 set. Okay? No?
But if x and y are 0, then z could be negative also.
Yeah, only in this case. Yeah, only in this case. This, if z is positive and these two, so I should say, if, x squared plus y squared is greater 0, not both of them are 0, and z could be in minus infinity 0 if x equal y equal 0. And this was the tricky thing about the z-axis, which is sitting here in these two pieces which arise along these lines, go to infinity and keep this in the interior. But this here is something artificial, because if you, for example, write a parameterization of this surface, the negative z values disappear. But here we need it, and so we decompose into strata. So we have the big stratum, now I call it x, is given by the points in W, where y is is not equal to 0. Yeah. And this, I claim, is the regular stratum, because then this does not vanish for all these points. And if y vanishes, then also x vanishes. This animal seems to love us, yeah? It appears every day, just waits for us. Maybe we have to do something dramatic in order. And so this is what I called W regular. This is a surface. And then we have the singular strata. Let's see, y greater and smaller is just 0, 0, z, where z is greater or less than 0, right? And then, of course, we have a last stratum, z equal 0. This is forced upon us because of the condition of the frontier. This we have already discussed. So now we want to know whether condition B is satisfied, of course. And so then we have to calculate a little bit. There are several cases. Oops, but maybe it disappeared. There's a typical aspect of such things. No. Why is this so long? It's not the right thing. So which is a nice case to study? Yeah, so let's take the case of Z, because this is a little simpler. So Z, which is just the point 0, is contained in X bar. That's clear. And now we want to see to check B. So what do we do? So we take a sequence I should not call it X now. Let's say a sequence Pn contained in X. And then I can write Pn is equal to plus or minus, because y is not equal to 0, plus or minus y z. This is also not true. The square root of z. And this was what brought me to this. So in X, z cannot be negative. And then we have y and z. And everywhere an n. And this goes to 0. So in particular, Zn goes to 0 and Yn goes to 0, but then automatically also Xn. And then we want that the tangent spaces, Tpn, converge to some space tau. And we want also that the connecting line between Pn and 0, this is just Pn divided by the absolute value. So what is this? This is plus minus yn square root of Zn, Yn Zn divided by the norm. So this is Yn squared times z and another Yn squared. So we get this here plus Zn squared. And we have to kind of normalize this. So the interesting thing is that Yn is not equal to 0. So we could divide by Yn here. So this we do. And so then what remains here is Zn plus 1, which is harmless because Zn goes to 0. And here comes something at first sight uncontrollable. Zn squared divided by Yn squared. And here we have plus minus. This drops out in two places. Zn, 1. And here again, Zn divided by the absolute value of Yn. But since Yn is not equal to 0, this will be positive. Yeah. Or could be 0. Yeah, important is, but at least greater or equal to 0. So now we have to make a case distinction. First case, this expression Zn over Yn is not bounded. Yeah, but this thing here is supposed to converge. So we may select a subsequence, and those conditions don't change if I take a subsequence. If it converges, then it converges for every subsequence. So without loss of generality, I assume that this goes to infinity. Goes to infinity. Okay? First case. So what will then happen? So then we take the first part. If this goes to infinity, the whole thing goes to infinity. I divide Zn by the square root of Zn by this, and this goes to 0, because Zn goes to 0, but these are bounded. So what happens here? Pn over the norm of Pn converges to a simple vector, as it seems, 2 times 0. And what happens here? So here we have this one divided by this one. This goes to 1. This goes to infinity. So this converges to 1. So we get this vector, which is just unit vector number 3, which is unavoidable in this case, the only possibility. So now we have to see what happens to the tangent space. What we should show and essentially in this way you always have to proceed. I mean, whenever you are given explicitly the description, the implicit description of the surface, you can do this. So we want that Tpn of x contains a vector. Now I have to, of course, to find, cannot take these letters for vectors anymore, so I have to take a Greek letter, or maybe this is more fun. I take a capital Greek letter. So we want to find these vectors such that they converge to E3 as n goes to infinity. Each tangent space contains such a vector which converges to this one. Then condition B is satisfied. Okay, how to do this? Well, we know the tangent space. That is the nice thing. The space Tpn. So it is equal to the vectors of the form alpha, beta, gamma, such that this is orthogonal on the differential. Okay, so we have 2 alpha xn minus 2 beta yn minus gamma yn squared equal to 0. And I'm completely free in choosing these 3 numbers. Pardon? Oh. No, I mean, this is the differential. The second part, oh, yeah, that's true. Yeah, you mean, right? This is true. Yeah, it's very difficult to translate this from one board to the other. Okay, so it would be an intelligent idea. I mean, these are really also, should also have an n, yeah? Because I have to make a different choice at each point. So what would be a good idea is to try gamma n equal 1 or minus 1. Doesn't matter, we could put it equal to 1. Because then I have a certain hope that the other part disappears, and in the limit I get the vector I want, right? But of course I have to satisfy this. So then we have here minus yn squared. And here we should again use what I did before, that this is yn times the square root of Cn. Okay? Now you see there's a certain similarity, and this condition obviously requires that all the Zn are non-zero. Yeah? So Zn will be greater 0. So for example, I could put alpha n equal to plus minus yn divided by the square root of zeta n. Yeah. So what can I do here? So then I would get here, this term would be equal then, okay, let me write it in this way. Alpha n xn equals yn squared. Now, of course, you see what you have to do. Beta n, now we have to take a constant, c, let's say, times yn over zn. So the c has to be chosen in such a way that everything becomes 0. So we get 2 here minus c minus, okay, let me write it. The devil is always in the detail. This is the trouble. But what is, and of course with this constant cn, so we have minus 2 cn yn squared. And now you see that you can determine uniquely, namely cn equal 1/2, and you get 0. And then the condition is satisfied. Yeah? So the idea is, if you have an explicit description of the tangent space, you play with it until you find something that converges to the prescribed vector, which is this here. And all the other cases are similar. I mean, a little bit more involved because you have 2 non-vanishing terms in the other case, but I think we need not repeat this. This was a nice idea. Okay, so this strange thing, so the Whitney umbrella is a, yeah, so I did not give a name to what comes out of all this. Where could I put this? I can remove the umbrella and find my sponge. Remove this here. So if these axioms are satisfied, then W is called a Whitney stratified space. So in this I abbreviate very suggestively W and S. Not WSS. This one is too much. Yeah. Whitney stratified space. Of course, you can introduce here the skeleton of the strata which are bounded in dimension. I explained last time what the dimension is of a stratum. Well, that's obvious. And the dimension of W is just the supremum of the strata and defines the top stratum, or the union of the top strata, if you like. So in particular, these spaces are in general not pseudomanifolds, because they always will have strata of codimension 1, as here the z-axis for the 2-dimensional surface. Yeah? So this is not very similar to a simplicial complex with the faces smoothed out along the edges, and also not to a manifold with boundary. Yeah, the umbrella looks quite different from a manifold with boundary, quite different. So one would like to understand these connections, and especially, so here I complete my sentence. It is a Whitney stratified space. And Whitney made lots of other examples where conditions are satisfied or not satisfied. Yeah? And as we discussed it yesterday, you cannot master this material in any way unless you study lots of examples. It is too difficult for our brain just to imagine, unless you are Tom or Whitney, then it's probably, but they did also thousands of examples. No, this is, the matter is too complicated. And Tom made the first big discovery concerning the meaning of condition B. So, what did he, I mean, to master this, for example, to understand this point here, it is of course very natural from the point of view of geometry that you analyze a neighborhood like a ball, look at the pieces in the ball. And then we have done this. You see, this is really a cone with two disjoint submanifolds as strata. And so it's like two cones sitting over this point. And so it's already very close to the topological stratification. But what is the general situation? And so now you can consider just two submanifolds. You need not think of anything else. So consider XY submanifolds. And this always means embedded submanifolds of R mu, such that X is contained in the closure of Y. And take a point now. All these considerations are local, so you may assume by applying a diffeomorphism, a local diffeomorphism of R mu, which keeps the point X. Well, let me assume right away that this is 0. Then you may assume that X is equal to, so we enlarge this, R mu R mu 1 times, this is the common notation in the old papers. So the points of X are X1, X mu 1, and then you add as many zeros as you need in R mu, and they like to note it like this. Yeah? This you find in the old papers. Not anymore, but Mother also does this. It's a very suggestive notation. Well, then you have we have a natural projection pi R mu 2 X, which just sends the point with these coordinates to the one where you set all the others to 0. So this is the standard projection. This was not a question. Okay. So this is the standard model of a submersion, as we know. And what does it mean? So if we take Y here.
I'm sorry, I'm a little bit confused about the notation mu 1 and
Mu, sorry. This is correct. This is the correct thing, yeah. So this mu1 is anything.
What is the dimension of x?
Yes, this is dimension of x. So we could maybe also write mu x. It's more suggestive. Mu x is the dimension of x. And mu minus mu x is the codimension. And if I have a point in y, which is, let's say, near 0, then this implies that it can be written in the form pi of y, and then some y mu minus mu x, which is not 0. Okay? Because otherwise, maybe I should disjoin. Yeah, otherwise this is impossible to do. But we have disjoint things, and with this assumption, and then you see this is very, very nice. Yeah. Yeah, but this is not enough. This does not tell you too much, and the question is now, how does this submanifold Y approach the submanifold X such that all elements of X are limit points, but it remains disjoint? And you can easily imagine there are thousands of ways in which this can happen. And Tom's ingenious idea was to define a control function for this stratum. Control means it controls in a certain way the approaching of x through y. And this is a very natural function, which is normally called rho. Put rho of x, or y, let's say, equal to sum. J goes from 1 to, J goes from mu x plus 1 to mu yj squared. Okay? This is the basic control function, which is actually nothing but the distance of y to x squared. And the idea behind is that he observed that in this distance, generally in a Riemannian manifold, but let's just stick to our mu, you can conveniently express the continuity properties, not the differential properties. So he, of course, had observed that you cannot expect some smooth relationship in general between these sets in terms of condition B, as you see also already from the umbrella. It's a very, I mean, the umbrella would be a little easier, but you can make arbitrarily complicated such things. And he said, so let's try only to have a topological condition. So this was the first step, but then he discovered this fantastic theorem. If in this situation, the situation I just B holds, then and we should say no, B holds at this point x. How did I call this point? X, yeah? I didn't call it at all. At a point x in x, then
Yes, I think you assumed it to be 0, right, over there.
oh yeah. Yeah, here
Or you want to...
I could say at that point, yeah. the generality I had destroyed before at the point 0. But 0 is in X. This we should leave. Then there is a neighborhood V of 0 in our mu such that, and this is conveniently called sigma. This is just the sum of these two maps from V to intersected with Y to, where does this go? To X, to R greater times X is a submersion. Smooth submersion. This is a strong theorem with a very nice geometric proof, which you find in Mather's paper, which I always carry with me. Just take this bulletin of the AMS, volume 49, number 4, from 2012. There, these most famous articles by Tom and Mather are printed, and so I need only and there it is, the beautiful lemma 7.3. So, and this is so nice that I cannot even make it worse. This you should study for yourself if you are interested. But this is rather a surprising result. Yeah?
Is this what's always called Tom's first isotopy lemma?
No. This is a long time before that. It's the basis for it. Yeah, so this is really the breakthrough.
Right.
Yeah. So that in spite of all these possible complications, this will always be true. Now, this is actually a transversality argument, and condition B just gives the one vector you need to get transversality. It's very elegant, very elegant. Also, I mean, to study this helps you to understand why condition B is actually needed. You know, so here you see this is a fantastic application. Now you have something which you can do, which you can handle. But you should now think again of a manifold with boundary, like this here. And this is, of course, true. Namely, the color gives you such a submersion. Actually, it's an isomorphism. And an isomorphism which extends down to the boundary. This is far from being true here if you think, for example, of the fast spiral, the spiral that goes outside. Yeah? It is also true here. Yeah? Amazingly enough. It is true. You get a submersion. I mean, for the spiral, this does not matter because you have only one point. But this here is a submersion on the open interval. If you take the point 0, then everything is destroyed. Then the tangent vector will rotate all the time. Cannot be any convergence there. Yeah, so of course the people have asked about the converse. Yeah? Is there a converse to this? Which would mean that a certain version of condition B is actually necessary and sufficient. And this happens to be true, but it's extremely tricky. The dissertation of David Trotman So now we have to be, is still, the setting is still in Rn. So x, y, disjoint submanifolds in R mu. And now I have to put it x. X is a point in X and contained in Y bar. Then choose a C1, and this is very important, C1 chart phi with which puts x into the standard position. This is the position I described on the other board. And then we get sigma phi equal rho phi, the same function I defined on the other side, and the projection p phi, which is normally non-trivial. And then the assertion is, so condition B tells you that if you have such a chart, then sigma will be a submersion. Then if for all C1 maps, C1 charts, phi, sigma phi, now you take V phi, I mean each phi defines another neighborhood of X intersected with Y to the stratum X and are greater. So for all C1 charts is a submersion for sufficiently small. So if you have phi, you can find this V phi, small neighborhood V phi. Then condition B holds. At X. Yeah, at first sight you think, well, this is not such a big deal, but I have to put a warning here. I mean that this is the important thing. For all C1 charts, phi, the statement is false if you allow only C2 charts. Okay, so it really depends on the loss of regularity. So C1 is the minimal regularity with which you can achieve this continuously. And so you can make a counterexample to the assertion for C2 charts. This is kind of extremely subtle. Yeah? And the proof is very difficult. Depends on perturbations of foliations, which put small perturbations. And then you need a mechanism that detects these perturbations. And this is translated because you have the neighborhood is foliated by the rho spheres. This is the foliation. This you perturb, in a nasty way, and then this condition detects it, and C2 does not. So I mean, it's a very short note, 8 pages or what, but there are many other papers behind. So these people did not repeat their whole work each time when they proved a new paper, but just said, look there, yeah, there are the. So, but I think this gives a good impression of the character of condition B. It is extremely subtle. But it has a strong implication. I mean, this way, that it is sufficient to achieve this, is relatively simple. You can read this during the Tagesschau or something. It's just a proof like this. But the geometry, you have to make clear to yourself what the geometry means. But this here is not at all trivial. I mean, this would take several lectures to expose this proof. But it shows why people were not too happy with these axioms. Even though they are fantastic short description of what you really want to do, it is not easy to work with them. In particular, it is, and Tom writes this in his very first paper, that you cannot expect to have good morphisms. Yeah? You can define immersions and submersions onto such spaces, but maybe a combination of both. Submersion after immersion, but that's it. Everything else is not reasonable. It destroys the structure of the objects. So it's not categorical, but of course one tries to find certain aspects which are. Okay, and so unavoidably, people had to do an abstract theory in order to prove more far-reaching results, and this is essentially Thom's isotopy lemma. It's kind of awkward because all the nice constructions in topology, differential topology, like forming the double, you cannot do with these things alone. Because if you do this, the double construction is actually very useful. Let's say you have a manifold with boundary, and you could then think about a Whitney stratified set with a boundary which is also stratified, and you want to put them together. Then you have to have this collar, which you extend. The collar defines you this boundary defining function. If you take the gradient the way I described it yesterday, then you have an inward pointing vector field. You can integrate it. Then you always have 1 in differential topology, so you get a flow. And if you put these two things together, what you do is you let it flow backwardly in maybe I should write this more forcefully. Let's say these things are all like this. Yeah? So then if you reflect them, they show in this direction, and you don't think that this is smooth. So you reverse the orientation, so you get a flow from here to here. But now you have to be very careful. So you have two open manifolds which are joined here. Here you have the color, which gives you now a homeomorphism to minus 1, 1 times the boundary. And so you construct an atlas taking all charts from the interior. Well, then you have a very good, and the same on this side. And then you compute the transition functions, and you see no transition function will touch the boundary if you try to understand smoothness. And so this is a smooth structure, even though it looks awkward. Yeah? And no matter what vector field you take, they're all equivalent. So actually, they are isotopic. You can deform these two things into each other. But this subtlety has to be kept in mind. Yeah? This is, and this you can do for a stratified space, I mean for a Whitney stratified space. The reason is that now you need vector fields which are tangent to the strata. Yeah? The strata which are coming in, let's say, in the, let's think about this being smooth, but you have some strata going along here. Then you want them to be tangent to the strata, and then the flow will not extend smoothly to the whole thing. Yeah? So you cannot get this as a map in Rn. You have to stick to this. The Thom control shows, however, that this flow can be extended continuously to everything. But to do this, you need a more general setting. And this setting now goes like this. This you also find in Mather's paper. And I mean, Mather never says anything that he doesn't prove. So he does not speculating, nothing. Very different from Thom, who always gives explanations. No, he is completely dry, but extremely precise. And so you can do now the following. You start with this, but then you need a topology for this space. Yeah? Otherwise, it doesn't make sense. And so, of course, you take a lot of Rm, mu, or let's say any smooth manifold. And of course, we take as much as we can. Yeah? And this would be that W is a locally compact second countable Hausdorff space. In particular, paracompact and normal. So these are the ingredients you need for the topology of manifolds. You also find wide varieties of assumptions in the literature, like separable and metrizable. Metrizability is a consequence of normality. Yeah? So that's okay. Not going into this any further. So then these axioms make sense, right? Do this as before, but this doesn't make sense. Where should we embed? Yeah. So you put here, or you get from here that these pieces are always locally closed in the whole thing because of this condition. Yeah, this means that the boundary of a stratum is closed, and therefore, as I wrote it down yesterday, each stratum is the intersection of an open set in W with a closed set in W. This is good. And so what we assume here, so X is a topological manifold. This is perfectly compatible with what we have. X is a topological manifold in the induced topology from W with a smoothness structure. So that's an atlas, smooth atlas structure. And now we know, whether we like it or not, that the smoothness order plays a role in all these things. And so it could be any lambda greater or equal to 1. Yeah, unfortunately, this cannot be translated in any way into the new situation, right? You can do it if things are, these strata are lying in some common manifold, or if you can represent it in some manifold, but otherwise you cannot. So, therefore I should, maybe it's not confusing if I leave this in this way. So there are control data. So this is essentially what I just did in these simple cases. So Tx, rho x, pi x for each stratum or each pure stratum. And what is it? So this is Tom's fundamental idea, where, let's say, A. Tx is an open neighborhood of x in W. Just any. B, pi x is a continuous retraction of Tx onto x. That means pi x is a continuous map of Tx, which if I restrict it to x, it is the identity. Okay, or you could say it is surjective, and if I apply it twice, it's the identity. It's no, it's a pi. It's an idempotent. Okay, so you see this is a relatively weak model of what we had before so far. And then the rho x No. I don't have it because I just take an open subset in this. Yeah, in the Euclid.
All of the strata have such a smoothness structure, so one could say the restriction of pi to the various pure strata.
Yeah, but this would be.
But you don't.
No, no. It's very complicated then if you. But this is the, I mean, it's nice, but the dangerous, the strongest axiom is still to come. I mean, so this is very simple, amazingly rough, really, and rho x is again a function Tx to R plus. R plus, just to avoid confusion, is the closed half line, is continuous with the inverse image of 0 is equal to x. So I guess this is called the projection. And this has no good name, it's just called the tubular function. So there are control data, which means that if you're given this space W, then first you find a partition into manifolds, and then you have to define for each stratum such a tube. You would think this may not be so difficult, but now it becomes difficult. Namely, now you say sigma x equal rho x chi x tx2 are greater. Now, of course, we have to take out 0 times x is a smooth, so that means is a C lambda submersion. And then it has all what you want, yeah? But first of all, it's just topology. And you need this, you need the continuity where, of course these are different strata, and on each stratum you have a smooth restriction, a submersive. So everything is higher dimension, yeah? So this implies if x less or equal to y, then the dimension of x is less than the dimension of y, which is very important. Many points.
Is it correct that you wrote there are greater than 0, or should it be r plus?
Not r plus. No. It should be. I mean, you have seen this in the condition B for the Whitney umbrella. This would utterly fail if you include 0. I mean, of course, you could write here 0 because, sorry, this is Tx intersected with y. This is, of course, for any y, sorry, always happens. Yeah. This was exactly what you meant. All those which come near, then the greater ones, and these restrictions are have x as limit points, and of course x itself is not touched here because y is disjoint from x, and it could not be because this is the set of singularities. Yeah, very good. Maybe at this point we could stop first of all and ask ourselves what's happening in the Whitney stratified case. Yeah? So how do you construct this? And actually, basically, I have done this. Yeah, you give this, you do this construction locally with a suitable chart, and then you construct a tubular neighborhood, and Mather is extremely careful in defining the most general tubular neighborhoods. It is not sufficient to say, okay, I take a Riemannian metric and I take the normal bundle and the normal exponential map. This is one tubular neighborhood, but you really have to take any vector bundle over, let's say, any real vector bundle over the manifold. You put a norm on the fibers, then you can say what is the epsilon ball in that bundle. Then you assume that you have a diffeomorphism from C lambda diffeomorphism from this picture to a neighborhood, which is called then a tubular neighborhood. This is the way a tubular neighborhood should arise, and this gives you some properness conditions in the embedded case, in the Whitney case. The properness here is a bit more tricky, in that you have to work by hand, but if you have local compactness, everything is not so difficult. We need not discuss this. So then this becomes the projection. We put these things in these standard notation in the case of a Whitney stratified set. And then we have seen, this was Tom's result, that you actually have a smooth submersion. C lambda greater or equal to 1. Now you understand that this is very difficult. If you want to understand condition B, but in praxis, you can work with C infinity for most cases if you want to do analysis. And you can put yourself in a more comfortable situation. So this is understandable. Now there comes a set of axioms which I do not want to explain so well. Now we have to have compatibility conditions. Between Tx and Ty if Tx intersected Ty is not empty. Yeah, so then, I mean, I will probably not use this, even though it's important. So maybe we can leave it like that, but you can find this in Mather section 8. And he is very careful and calls this abstract Whitney stratified sets, which are abstract in the sense of topology. You have a topological space which is decomposed into pieces. The pieces are topological manifolds with a smoothness structure. And then this is the most important thing, you have these control data. And for many applications, for example, in connection with the isotopy lemma, you need this compatibility. Yeah, so that, like if you have two strata and you have the projection for one, and this point is also in another stratum, then you can first project onto the other stratum, then project down, and you get the same result. That's such commutation rules, which are, if you draw yourself some pictures, they are natural, but it takes a while to write all this carefully. And then, in terms of mappings, Mather makes only a very, very tiny, allows a very tiny variation, namely that you may refine these data by making the tube smaller. Nothing else. Yes, and okay, but now you have spaces which allow at least some maps. Yeah, so now these spaces we call AWS, abstract Whitney stratified. And of course, you want to know what is the relation to and one part of the answer I have already given. Namely, we know that a Whitney set, Whitney stratified set, will satisfy these axioms, because the crucial one is this here, and this is Tom's result with a refinement of Trotman, which is not actually not needed. But the other question is, to some extent, maybe entirely open. And to make this a sensible question, we have to to say what this means. Yeah? We have to say what this means. So we have to define smooth maps of such objects, let's say into our mu. So define suitable maps, let's say psi a ws to R mu. Maybe this is too rough. So here we have an element, and we map this abstract topological space into R mu, and such that psi of W is a Whitney set. Yeah, so this would be, in a sense, the completion of this theory, but does not seem to exist yet. And how do we? So what do we have to do with the psi? So just look at this. Psi W to psi of W. I mean, I lose too much if I don't require that this is a homeomorphism. Is homeomorphism. Then psi restricted to any x again sitting in R mu. So this is a C lambda manifold, and this should be also a C lambda manifold, and this should be a smooth embedding. Yeah, so is an embedding of C lambda manifolds. There's not much more than what I can require from a general map. Yeah? So what I would get from this is that the image has a decomposition S psi of W equals psi of, let me put it like this, psi of x in S of W, which is again a decomposition by C lambda submanifolds. And this tiny exercise is a simple consequence of the continuity of psi, that this is preserved, this property. So we have the group 1 of the Whitney sets, right? And 2a says just this, each psi of x is an embedded submanifold of R mu. This we also have found out. So what remains is the condition B. So how should we call these maps? These are stratified diffeomorphisms, yeah? Stratified, or C lambda stratified. Should we say diffeomorphisms or homeomorphisms? I think this is better to say it's a homeomorphism, because this puts the whole, refers to the whole topological space, and on each stratum we have a C lambda embedding. So,
C lambda stratified embedding.
oh yeah, embedding is like even better, yeah? Yeah, good. Because it's an embedding also on the strata, yeah? And so we can make now the question precise. Precise question. If W, and I find it reasonable to restrict now to compact objects. We have finite set of strata, and it's complicated enough. Yeah? If W is a compact AWS, does there exist a stratified, C lambda stratified is a, so I should say here C lambda, because we should, I mean, Mather says always smooth, and says smooth means C lambda, for lambda between 1 and infinity. But let's point it out here. C lambda stratified embedding psi W are mu, and mu is of course a dimension which depends on W, such that psi of W is a Whitney stratified set. And here we have to put a question mark. So that means, first of all, we want an embedding for the whole thing, and then we want to verify condition B. So I don't have much time, but maybe I remind you here of the Whitney embedding theorem, which is quite important. At least I think it's the right idea to use and to modify. Whitney embedding theorem. The case kappa of W. The complexity I can define as before is 0. So that W is a compact manifold So then do the following. So, construct a finite cover. A finite cover by open sets Vj, which contain, so I don't know, is this notation allowed in topology, the double inclusion. I mean, in analysis, this means it's compact. The closure is compact and sitting in there. But I can do it like this. Contains uj. J goes from 1 to R, where uj is an open cover. So it's a smaller cover with uj bar contained in Vj compact. And it's clear, I mean, this is complicatedly written, but it's clear what it means. You take a point, take a neighborhood which is diffeomorphic to Rn, and take the pre-image of the unit ball. Then, for example, you have this. Okay, so this is, I call U. And choose no, moreover, maybe I should do this differently. Let uj phi j be a smooth chart for this manifold, and fj a bump function for the pair Vj, Uj. That means Fj is a smooth function with compact support in the big one, which is 1 on Uj. This is, I mean, that even for a topological bump function is defined this way. Then this is the very nice idea. Then psi so locally you take the embedding here in Rm, but of course this is not defined on the whole manifold, so you cut it down by the bump function. And this you do for all these parts, with the effect that these maps are smooth maps into some R mu. Actually, they all go into R M if M is the dimension on, let's say we call it W, RW. But then you also add these bump functions. And this is C lambda, or in this case, let's say C infinity, or C lambda stratified embedding. But this is, of course, not necessary in this case, but to show that this is actually what we want. And this is your homework for tomorrow, but it's also very easy. And this idea has a big drawback, which has distracted people somehow from using this, because you cannot control the dimension of the embedding space, or the codimension in terms of what you want is the smallest embedding. And so Whitney used completely different techniques to first construct a big embedding and then reduces this to smaller ones by some transversality arguments. But for the stratified maps, it's better just to stick to this. And this I will explain tomorrow. Now it's enough. Thank you.